Today, we're drilling down into one of the most critical, yet kind of hidden components of modern engineering, the science of mud. So just imagine for a second, you're drilling a hole, not just a few feet deep, but miles straight down into the Earth's crust. It's an incredible feat of engineering, for sure, but it also creates a massive problem. What's to stop the immense pressure of all that rock from just crushing your hole shut?
The answer, believe it or not, is mud. But this isn't just any old mud. Oh no, this is a carefully engineered fluid that forms a thin, protective layer that we call a mud cake right on the wall of that wellbore. It creates a vital barrier between the drill and all that porous rock.
Okay, so here's our game plan. First, we'll get up close with this protective skin. Then, we'll dig into why the quality is so critical. We'll check out the machine they used to test it, walk through the pressure test itself, and then we'll decode what those results actually tell the engineers. All right, let's get into it. Part 1, understanding this protective skin, the mud cake.
So the technical term for this is filter cake. As the drilling fluid, the mud, is pumped down the well, the liquid part gets squeezed into the tiny pores of the surrounding rock by some serious pressure. But the solid particles, they're too big to fit, so they get left behind, building up against the wall and forming this cake.
And this thing has two vital jobs. First, it's a sealant. It stops the expensive drilling fluid from just disappearing into the rock. And second, it acts as structural reinforcement. It's literally plastering the walls of the hole to keep it from caving in.
Now for part 2, you gotta know, not all mud cakes are created equal. The quality of this super thin layer has huge implications for safety and for the budget.
And the difference is pretty stark. A good mud cake is exactly what you're hoping for. It's thin, so it doesn't clog up the well, but it's also incredibly strong and basically waterproof. A bad one, well, it's the total opposite. Thick, weak, and it leaks like a sieve.
And the consequences of getting a bad mud cake, they are not pretty. We're talking about an unstable well that could just collapse. It can get millions of dollars of drilling equipment permanently stuck miles underground. You lose enormous amounts of drilling fluid, and all of this adds up to a project that takes way more time and costs way more money.
So, how do you make sure your mud is going to work before you pump thousands of gallons of it into the ground? Well, you test it. And that brings us to this key piece of gear, the API filter press.
This is the one. It's the industry-standard device used to test drilling fluid. Its whole job is to simulate the intense pressure and filtration that happens miles down in the well, but to do it right here in a controlled lab.
You know, when you see it broken down like this, it looks a lot less complicated. You've basically got a sturdy cell to hold the mud sample, a pressure source like a little gas canister to apply all that force, and then right at the bottom, a piece of filter paper that acts like the porous rock you'd find downhole.
Okay, we've met the machine, now let's run the test. This is where we get to simulate what's really happening deep underground.
The whole process is actually pretty simple, and it's standardized. You just load your drilling fluid into the cell, you seal it up, and you hit it with pressure. As that pressure squeezes the mud, any liquid that gets through the filter paper, that's called the filtrate, drips down into a little measuring cylinder so you can see exactly how much you've got.
And the standard test is always run for the same amount of time, exactly 30 minutes. That standardization is absolutely key, because it means engineers anywhere in the world can compare their results and know they're talking about the same thing.
So the really crucial point here is that this whole setup, the cell, the pressure, the filter paper, that 30-minute timer, it's all a carefully designed simulation. It's a tiny, controlled version of the massive, chaotic environment happening thousands of feet below our feet.
Dang, the timer goes off, the pressure's released. So, what did we learn? Time for our final section, decoding the data.
When the test is over, engineers are looking at two main things. First, the total amount of filtrate they collected. In other words, how much liquid did the mud cake let through? The lower that number, the better the seal. Second, they literally take out the filter paper and measure how thick the mud cake is. The goal is thin and dense.
And this is where the physical world meets the world of data. The engineers take that physical measurement of the cake's thickness and they compare it to a graph that shows how much fluid was collected over time. That graph tells the whole story of how well that mud cake did its job. And a key part of that story is something called spurt loss. This is that initial gush of fluid that gets through right at the start, before the solid particles have had a chance to pack together and form a good seal. A really good mud formula is going to have a very, very low spurt loss.
What's really fascinating is the physics behind all this. See, the rate of fluid loss isn't constant. It's proportional to the square root of the time. What that means is, as the cake builds up, its ability to seal increases exponentially, and the fluid loss slows down to a trickle. That is the sign of a stable, effective mud cake.
So when you step back and look at the big picture, it's pretty amazing. The success of a massive, multi-billion-dollar drilling project can hang entirely on the performance of this slimy layer of mud that's just a few millimeters thick. It makes you wonder, doesn't it? What other tiny, seemingly small details have a massive impact on our world?